Welcome to The Explainer. Today we're diving into something totally fascinating and honestly kind of urgent in the AI space. We usually picture AI as this all-knowing brain, right? Confidently giving us answers, generating wild images, navigating our cars. But what actually happens when the AI doesn't know the answer? Today we're unpacking exactly that, the science of making artificial intelligence doubt itself. Because right now, this is a massive blind spot. Modern AI models are incredibly powerful, no doubt about it, but they have a really dangerous flaw. They are wildly overconfident. Even when they're completely, utterly wrong, they'll just spit out an answer with absolute certainty. And if we're going to deploy these models safely out in the real world, they urgently need a built-in way to quantify exactly what they don't know. Okay, let's dive into this. Here's our roadmap. We'll start with the AI uncertainty problem, then look at Dempster-Shafer Theory, the types of AI uncertainty, Monte Carlo Dropout, ask is MC Dropout reliable, and finally, the high stakes in real life. All right, part 1, the AI uncertainty problem, moving beyond point estimates. And this brilliantly illustrates why a single, rigid prediction just doesn't cut it anymore. If you notice that blue line, that represents your standard AI model. It just hands us a single, rigid point estimate, basically a definitive guess. But check out the red line. This is an uncertainty-conscious model. See that shaded red area wrapping around it? That's an uncertainty interval. So instead of just blurting out a single answer, the model's giving us a prediction range. It's showing us its own variability and its confidence level. Whenever that shaded area gets wider, the model's essentially raising its hand and saying, hey, I'm kind of shaky on this specific area. Moving on to part 2, Dempster-Shafer Theory, the classic detective story. Well, long before we had these massive deep neural networks, scientists still needed a solid mathematical framework for juggling conflicting information. Think of it like a classic locked room murder mystery. Imagine a dark room, 4 people inside, A, B, C, and D. The lights completely cut out, and when they come back on, person B is dead. Nobody came in, nobody left. So how does an AI logically process that? Using Dempster-Shafer theory, it doesn't just jump to one conclusion. It explores mutually exclusive possibilities. Step 1, maybe it was A, C, or D acting alone. Step 2, maybe it was a duo, right? Like A and C together. Step 3, all 3 were in on it. Or step 4, none of them did it and it was some crazy elaborate trap. The whole point is, this theory lets the system hold all these clashing pieces of evidence in its head at the exact same time. The real engine behind this kind of deduction is called the mass function, written out as MK. It's a mathematical tool that essentially assigns a degree of belief to these sets of hypotheses. Now, what makes Dempster-Shafer so incredibly cool is how it deals with total ignorance. In standard probability, you're usually forced to make assumptions just so everything neatly adds up to 100%. But the mass function? It doesn't do that. It lets the actual evidence build up into what we call belief and plausibility, completely avoiding those forced assumptions. It just narrows down our suspects using only the hard evidence we actually have. Okay, part 3, types of AI uncertainty, from math to neural networks. Let's see how this translates over to modern deep learning, because we really need to categorize the specific types of doubt an AI actually feels. In the machine learning world, uncertainty basically falls into 2 main camps. On the one side, we've got epistemic uncertainty. Think of this as model uncertainty, a literal gap in knowledge. It happens when the AI just hasn't seen enough data to connect the dots. But the good news? It is totally fixable. Just feed the model more data, and that epistemic uncertainty drops. On the flip side, we have aleatoric uncertainty. This is the inherent noise or randomness in the world itself. We're talking about things like static on a camera lens or natural biological differences in medical scans. And here's the kicker. No matter how much data you throw at the AI, you literally cannot get rid of aleatoric uncertainty. You can only model it. Now, what's really interesting about this slide is how we try to physically capture that uncertainty right inside the architecture of the model itself. This is a Bayesian neural network. In your standard neural net, the connections between neurons, the weights, are just fixed single numbers. But a Bayesian network is different. It treats those weights as entire probability distributions. So it's not learning one rigid parameter, it's learning a whole range of likelihoods. This is a huge deal because it allows the network to naturally express its own doubt, giving us a full distribution of predictions instead of just one guess. But, yeah, there's always a catch. Calculating all those distributions requires a massive, massive amount of computing power. Which brings us to Section 4, Monte Carlo Dropout, the modern deep learning solution.
Because Bayesian neural networks are just so incredibly heavy and expensive to run, developers desperately needed a practical workaround. Enter Monte Carlo, or MC Dropout. This comparison really highlights why it blew up in popularity. So traditional dropout is a pretty classic technique used while training a model. It randomly switches off or drops out certain neurons. This stops the model from just blindly memorizing the data, which prevents overfitting. Usually, once training is over, you turn dropout off and boom, you get a single fixed value. But MC Dropout flips the script. It actually keeps that dropout function turned on during testing and inference. So by running the exact same input through the network over and over, with different neurons randomly shutting off each time, it essentially creates a whole ensemble of thinned-out networks. The result? You get a distribution of slightly different predictions. The average of those is your final answer, and the variance between them? That becomes your estimate of the model's uncertainty. It's brilliant because it's computationally cheap and super easy to set up.
But wait, here's section 5. Is MC Dropout reliable? The plot twist. I mean, it sounds like the perfect silver bullet, right? But science never stops, and some recent empirical tests have thrown a massive wrench in the works. A recent paper dropped on Archive actually put MC Dropout head-to-head against traditional Bayesian models like Gaussian processes. And the researchers found a pretty glaring issue. They stated, quote, MC struggles to accurately reflect the underlying true uncertainty, particularly failing to capture increased uncertainty in extrapolation and interpolation regions, end quote. So what does that actually mean for us? It means that when you ask the AI to guess about data it has literally never seen before, the exact places where it should be super uncertain, MC Dropout often just doesn't show that doubt. It acts way too confidently right in its own blind spots, and that is exactly where we need it to be cautious. The researchers mapped out exactly why MC Dropout was failing these controlled experiments. First off, it showed a constant variance across the input space. So instead of its uncertainty getting wider in unknown territories, the metric just stayed totally flat. Secondly, because of that flat line, it completely failed to capture epistemic uncertainty. You know, that crucial lack of knowledge we talked about earlier. Third, it turns out its uncertainty profile was heavily dependent on random initialization seeds, so the doubt it was reporting was actually being driven more by the random math at the very beginning than by the real evidence. Long story short, it's a clever approximation for sure, but it absolutely does not behave like a true Bayesian postulator model when you actually push it to its limits.
Bringing us to our final section, high stakes in real life. Why uncertainty matters.
You might be wondering why researchers are obsessing over these tiny mathematical nuances. Well, out in the real world, this is absolutely not just some academic debate. So the crucial point is how this literally impacts human lives. Just think about autonomous vehicles trying to navigate a crazy, unpredictable city street, or AI tools analyzing a patient's cancer scans. These systems are operating in dynamic, incredibly high-stakes environments. If a self-driving car rolls up to a bizarre, blocked-off intersection it's never trained on, it has to experience a spike in epistemic uncertainty. That mathematical doubt is the exact trigger that tells the car, hey, slow down, or hand the wheel back to the human. And if a medical AI hits an ambiguous scan, accurately measuring its own uncertainty is literally the difference between making a fatal misdiagnosis and flagging a doctor for a second opinion.
Which brings us to our final thought for this explainer. We are rapidly weaving deep learning into the very fabric of our everyday lives. But knowing what we know now about how hard it is to actually measure epistemic and aleatoric uncertainty, and seeing the real mathematical flaws in popular workarounds like Monte Carlo Dropout, we have to ask, can we really fully trust autonomous systems with our lives if we're still perfecting how they measure their own doubt? It is a massive question, and it's one the brightest minds in AI safety are scrambling to solve as we speak. Thank you so much for joining me to explore the incredibly fascinating science of AI uncertainty. Keep questioning the algorithms, and I'll catch you next time.